Okay guys, let's take a look at improper integrals for day 2. On this lesson, what we're going to be doing is we're going to be looking at the integral types from yesterday's notes, the ones that were on the right, where just by looking at it, just glancing at it, you can't tell that it's improper. You actually have to really kind of study it and notice that there are issues. This particular one is undefined at 0, so that would be right here. It would be considered, this is improper. What we want to do, basically this type, is when you have an infinite discontinuity at one of the bounds, either the upper or lower bound, or somewhere in the middle. Somewhere in the middle there's some kind of infinite discontinuity, an asymptote. Then we have an improper integral. So these are a little bit more difficult to determine, but when you inspect it, hopefully you will pick that up. So we will use the rules on that slide, on the right side from yesterday. We're going to use those rules to rewrite this. So let's take a look at the first one. On the first one, just looking at it, we can't tell that it's improper, but once we inspect it, we realize that 0, this particular function is not defined at 0, so we have an improper integral. So we're going to rewrite it. So we have the limit as a approaches. Now this was confusing students earlier. Let's talk about, these are one-sided limits. The interval that I'm interested in is between 0 and 1. That's the interval that we're camping in, okay? Am I going to be approaching 0 from the right or the left? From the right, because that's where we're interested. We're not interested in the left. We're not even messing with the left. So we're going to do the limit as a grows to 0 from the right of the integral of a to 1, and I'm going to write it in negative exponents, so x to the negative 1/3 dx. Okay, that's our rewrite. So we integrate that, we get limit a goes to 0 from the right. Our antiderivative is 3/2 x to the 2/3, and we evaluate that from a to 1. Okay, so this procedure is similar to yesterday. The setup is a little bit different, but the procedure is pretty much the same. We concentrate on the integral. We're going to evaluate the integral. So limit a goes to 0 from the right. We put a 1 in, and we get 3/2 minus, we do f of b minus f of a, so we put the a in. We get 3/2 a to the 2/3. And then we take the limit, and just kind of remembering back to limits, when we are dealing with a one-sided limit, our first option is always just to plug in that number, just to plug in the 0. If it works, great. If it doesn't, then we have to think about, well, what would 0.1 do? What would 0.01 do? What would 0.001 do? So this one, we just sub in a 0. This goes to 0. And this particular one converges to 3/2. Okay? Right here. So I add 1 to negative 1/3, and I get 2/3, right? Okay. All right. All right. Let's look at our next one. Okay, this one, same kind of issue. We are not defined on one of the bounds, the lower bound, so we're going to have to do the same kind of setup that we did on the first one that we worked. So this is going to be the limit as a goes to 0 from the right, and I'll write it in negative exponents, just easier to think about. A to 1 of x to the negative 3 dx. Okay, so we do the antiderivative. I add 1 to that, I get negative 2. I divide by negative 2, I get negative 1/2. So that equals the limit as a goes to 0 from the right of negative 1/2 x to the negative 2. I'm just going to write it like that. And we're going to evaluate that from a to 1. Okay. So then we do our f of b minus f of a. We put the 1 in, we get negative 1/2 minus a minus, so plus 1 over 2a squared. Alright, so let's take that limit. Okay, so this, it's clearly negative 1/2, that's not an issue. If I substitute a 0 in, that's going to be a problem, right? It's going to be 1 over 0. If I think about it as like a fraction like 0.1 or 1/10, 1/100th, if we fix the complex fraction, we're going to get a larger and larger number, aren't we? So this is going to tend to infinity. This is going to go to infinity. So this tends to infinity, so this diverges. Because again, I'm putting fractions down here, right? 0.1 or 1/10, 1/100th, and when I fix it, it's actually 10 and 100 and 1,000. Does that make sense? Okay. All right. So that's our first two. Hopefully we're all doing pretty well, right? Nothing crazily different from yesterday. Let's take a look at the few on the back. Oh, let me move that guy. All right, let's look at that first problem. Okay, so this one, let's see if we have any issues here. Yeah, on this one we have an issue on the upper bound, don't we? If I put a 27 in, that's bad news. So we're going to use our definition from yesterday to rewrite. So we get the limit as b approaches 27. Now, are we coming from the right or the left on this guy? From the left, right? Because the interval is on the left of the 27. From the left of, let's see, integral of 0 to b dx over cubed root of 27 minus x. All right. Now, I'm a big fan of, when we do the u substitution, I'm a big fan of changing the bounds, except for with improper integrals, because if I can change the bounds, but think about this. This is not a number. This is a letter. So when I sub the letter in, I'm going to get something with a letter in it that's more complicated than what I have. So I normally don't change. I normally put the x's back in on improper. You can certainly do whichever you want, whatever you feel comfortable with, but I normally put the x's back in on this. So we could do the u substitution in our head, or we could write it out, whatever we're comfortable with. U equals 27 minus x, so du equals negative dx. So negative du equals dx. I'm going to need a negative. We have limit b goes to 27 from the left. I'm just going to leave the bounds off because I'm going to have u stuff in here and I don't want to calculate the u bounds. So I'm just going to leave it blank for right now because I intend on putting the x's back in. And I don't want to mix the variables. I don't want to confuse myself. So I'm just going to leave it blank for right now. This is what, u to the negative 1/3. U to the negative 1/3. And there's actually a negative outside this integral. And then du. Okay, so we do the antiderivative of that guy, and we get 3/2. Let's see, we add 1 to negative 1/3, and we get 2/3. So we're going to multiply by 3/2. So limit b goes to 27 from the left. We have a negative 3/2. And I'm going to go ahead and put the x back in. It will be u to the 2/3, but I'm going to go ahead and put the u back in. 27 minus x. I have this that was generated from the u sub. Yeah. To the 2. Alright, to the 2/3. We're evaluating it from 0 to b. Okay. Is everybody okay? Alright, so we put the b in there and we get limit as b goes to 27 from the left. We have negative 3/2, 27 minus b to the 2/3, minus, well, it's actually a minus minus, so plus 3/2 times, I put a 0 in, I get, what, 27 to the 2/3. Okay, let's take the limit. When we take the limit, our first term is going to go to 0. And I'm going to be left with this kind of crazy looking thing. So cubed root of 27 is 3. 3 squared is 9. So it's 3/2 times 9, or what, 27/2. Okay, we okay on that one? We're pretty regular so far. Nothing crazy, I don't think. Gets a little crazy, but we'll be fine. On this next one, our problem is not on either bound, is it? It's in the middle. 1 is a problem here. So what I'm going to do, and certainly you don't have to do this step, I'm going to go ahead and split the integral first, and then I'm going to use the definitions. We're actually going to have to do 2 separate integrals for this, because our problem is at 1. Alright. So let's split it. We're going to do the integral 0 to 1 of this guy plus the integral from 1 to 3 of this guy. Okay. So I'm splitting the integral first. And again, you don't have to do that step. You can go straight into the definition if you want. Alright. So what we're going to do is we're going to, on this first one, again, the 1 is the issue. We have 2. Here our upper bound is an issue. Here our lower bound is an issue. So we're going to do the limit as b goes to 1. Now which side are we approaching on this one? The left. We're going to the left of the integral of 0 to b dx over x minus 1 to the 2/3 plus limit as a goes to 1 from the right of a to 3 of dx over x minus 1 to the 2/3. Now on this one, since it's so complex, what I would probably do is just kind of do my integration work on the side, you know, because it's going to be the same integral for both of them. I don't want to double my work. I would just go over here to the side and work my integral, and then I would come back and put the integral in and do the f of b minus f of a. So let's do that. Let's just kind of go over to the side. It would be like the integral of u to the negative 2/3 du. I mean, that's really the integral we're working, right? U would be x minus 1. So we integrate that, we add 1, and we get, what do we get, 1/3. So 3u to the 1/3 is what we have. Is everybody comfortable with that? And so I'm going to take this, and we'll just put the x back in. So it's really 3 times x minus 1 to the 1/3. That's really what we have. And that's what I'm going to insert back into here with the limits that we're going to evaluate. Just saves a little bit of work, or a little bit of space, I guess. So we did the integral. It was 3 times x minus 1 to the 1/3. We're going to evaluate this one from 0 to b. Then we have the limit as a approaches 1 from the right. And again, we have our 3 times x minus 1 to the 1/3 evaluated from a to 3. Okay, everybody okay? All right, now let's do our f of b minus f of a thing. So we have the limit as b approaches 1 from the left. I'm going to, f of b is actually b. 3 times b minus 1 to the 1/3 minus 3. Now I have a 0, so that's going to leave me negative 1 to the 1/3. Okay, plus. Then we have our other limit statement, limit as a goes to 1 from the right. We're going to drop the 3 in. That's going to give us what? A 2 to the 1/3 minus 3 times a minus 1 to the 1/3. Okay, is everybody okay? All right. So let's substitute. It looks like we can do direct substitution. We like that. I substitute a 1 in here. That tends to 0, doesn't it? It's going to go away. What is the cubed root of negative 1? Negative 1. And negative 1 times negative 3 is going to give me a 3. So that side gives me a 3. 0 plus 3. Okay, let's look on the right side. So 2 to the 1/3, that's some crazy decimal number. So I'm just going to write it as 3 times the cubed root of 2. And let's substitute our 1 in here. We're going to get a 0. And so this one converges to 3 plus 3 times the cubed root of 2. That's a wacky one, isn't it? Okay. Bless you. All right, let's look at our last one. In this one, we are looking at 2 natural log x, and we want to let R be the unbounded region in the 4th quadrant between the graph and the x-axis. They want us to find the area. So we're looking at 4th quadrant, and it's up here to 1. So we're looking at all this area in here. This would be an asymptote. So what we're wanting the integral from 0 to 1 of 2 ln x dx. That's what we want, right? But we recognize that ln x doesn't exist at 0, does it? There's an asymptote there. So this is an improper integral that we need to solve, with the lower bound being the problem on this one. So limit as a approaches 0. Are we coming from the right or the left? We're coming from the right. Integral of a to 1 of 2 natural log x dx. Now, some of you have integrated ln x enough times where you have it memorized. I'm not going to assume that. We would do integration by parts on this one. So let's do our integration by parts. Let's see, we would put ln x in the derivative part and 2 in the integral part. So derivative of ln x is 1 over x. The integral of 2 is 2x. So we ask ourselves, if we stopped, could we, and multiplied the bottom of the columns, could we integrate? And our answer would be yes. So we would stop, and this is our multiplier. Alright, so let's write that. So limit a goes to 0 from the right. Let's see, we have 2x ln x. And then we have minus, let's see, 2x times 1 over x is just 2. So minus integral a to 1 of 2. Now, to follow the integration by parts formula, we'd put like a little guy here. This multiplication part is not exempt from the bounds. It has to do the bounds also. And so you can put that there, or just remember to include it in the bounds in your answer. All right, so the integral of 2 is 2x. So let's see what that would be. So limit a goes to 0 from the right. All right, we put a 1 in here, we get 2 ln 1. I'm going to do the little multiplication part first, and then we'll move to that one. Then we're going to put the a in, so minus 2a ln a. Okay, that's the multiplication piece. That piece is done. All right, so here we have basically, when we integrate, it'd be a negative 2x. So I put a 1 in, I get a negative 2 times 1. I put an a in, so minus a minus, this will be plus 2 times a. Okay, I'll pause here for a second. How are we? You could do it all at once. You don't have to do them piece by piece. You could do it all at once. Yeah, and that's what I normally do. I just normally do this whole thing at once, but I want to make sure we realize that this is not exempt. That's why I did them separate, but you don't have to. Okay, so let's tackle this little guy. Well, a few of these things are pretty easy. Like 2 ln 1, I mean, we know that's 0. That's pretty easy. ln 1 is 0. And we know that over here, 2 times 0 is 0. Well, we know that, right? This one is the one that's just a little bit challenging because we basically have 0 times ln of, well, it's not really ln of 0, it's 0 from the right. So think of the natural log graph that's going to negative infinity. We basically have 0 times negative infinity. We have two ways to think about this. One is using the algebraic techniques that we learned several months ago. Remember the indeterminate forms? What do we do when we have like 0 times an infinity? What do we do? That's the other one. That's the other. What do we do? What do we do? Yeah, we try to make it do, we rewrite it to try to make it infinity over infinity or 0 over 0 so we can use L'Hopital. Okay, that's one way, and we can work through the algebraic way. Yes, we would have had to remember that. Sorry. That's the way it is. So actually, let's tackle it algebraically. So we have a procedure to do. And you may, well, from the sound of some of us, we may not remember this at all. So I'm going to remind you, think about this being over 1, and then we flipped him upside down. Okay, I'm getting like, what are you talking about? Okay, that's really what we did. Okay, to reach back in the dark recesses of your memory. So I'm going to treat this separately. We're going to look at the limits in pieces. So it doesn't really matter where the negative 2 goes. We'll just leave it up here. The ln a would be up here, and then we would flip this guy upside down, and he would be there. Right, so if I flip him back, okay, we hopefully remember. Maybe? Glimmer of memory? Okay, not yet. All right, so then we would put the 0 in here, and this guy on top is going to go to infinity, and the guy on bottom is going to go to infinity. And so we have infinity over infinity. So what can we do? L'Hopital. We can do L'Hopital. So I'm just going to it bothers me not having this down here. I know, it just feels bad, so I'm putting the limit down here. So let's do L'Hopital on him. And we get the limit as a goes to 0. Okay, so remember, L'Hopital, we do the derivative of the top, which is, what, negative 2 over a. The derivative of the bottom, that would be like a to the negative 1. So if we subtract 1, it'd be to the negative 2. Remember, we're doing derivatives, not integrals. Don't go backwards on me. We're doing derivatives, not integrals. Yeah, it's negative, what does it turn out to be? Negative 1 over a squared. Now, if we fix that complex fraction, are we okay? We have 2a. That's 0. This is going to tend to 0. So I have 0, I have 0, I don't have 0. I have 0. So I basically have -2. Pretty complex limit right there. Lots of fun. Fun with all the little parts, isn't it? Okay? All right.